All right, 8th grade, welcome back in. We're in your Eureka Workbook, Module 1, Lesson 2 today, multiplication of numbers in exponential form. And right below your little classwork section right here, you'll see some notes in general. If x, which x could be any number, is any number and m, n are positive integers, so m and n are numbers that are positive, then this statement right here, x to the nth power times x to the nth power equal to right here. Now look, let me show you this with actual numbers. Okay, let's use 2. Okay, let's say we have 2 to the 3rd power times 2 to the 2nd power. Well, in this situation, we can actually just add the exponents and get 2 to the 5th. That's all that this statement is saying. It's saying that 2 to the 3rd times 2 to the 2nd is 2 to the 3 plus 2 to the 5th. So right above over here, I'm going to illustrate why this is the case. So here I have 2 to the 3rd, which is 2 times 2 times 2, just putting that in parentheses for now, times 2 to the 2nd power, which is just 2 times 2. Given that the only operation happening in this statement is multiplication, we can use the commutative property to move all of these numbers around any way we want. So essentially we can take them out of their boxes. So now it's just a repeated statement of 2 times 2 times 2 times 2, which is 2 to the 5th power. Now check it out right over here. I'm gonna prove to you one more time. So we're gonna multiply 2 times 2 to get us 4 times 2, which is gonna get us 8. So we have 8 times 2 times 2, which is, we have 2 times 2, which is 4. 4 times 8 is 32. And if we try it over here in this form, 2 times 2 times 2 times 2 times 2, multiply the 2's, 4. 2 times 2 is 4. Times 2 is 8. 8 times 4 is 32. The commutative property dictates that when we multiply numbers with the same base, we can add the exponents together. All you're going to be doing in exercises 1 through 8 is adding up the exponents. Since we have common bases, 14, the base stays the same, and we just add these two exponents, 23 plus 8, which equals 14 to the 31st power. Okay, so I want you to do 2 through 7 and then stop at 8, okay? Give yourself 2 minutes on the clock. Pause it. We're going to go back and discuss 1 through 7 in just a second, but I wanted to start with exercise 8. Let x be a positive integer. And then they give you this statement right here. And you'll see that x is over here. It's the exponent over this -3 right here. So you need to figure out what that x value is supposed to be to make this statement true. So take a moment, try to figure out what you can get. 30 seconds, see if you can figure it out. That's very interesting, very good. You know that you would have to add 9 to whatever this is to get to 14. So we know that 9 plus 4, 9 plus 5, I should say, you can count up 9, 10, 11, 12, 13, 14, 15. We know that x needs to equal 5 in this situation. Now the question is, why did this question phrase it like this? Why did it have to be a positive integer? What do you think? Why would it phrase it specifically that way? Could this have been a negative integer? Okay, well, those are all very interesting responses. Later on, we're going to talk about negative integers. I mean, negative exponents, I should say. So don't stress too much about that. This needed to be 5. X had to be 5 here because 9 plus 5 gets you 14. All right, so for exercises 2, 3, and 4, they're literally just like the first exercise 1 that we did together. You add up the exponents and you maintain the base. This is what you should have gotten for all these. Let me know if you got something different. Maybe you added wrong. Then we come over to these ones with the variables in them. So were you tripped up by the fact that there were letters here? I hope not. It doesn't matter what the base is. We don't know what A is in this situation, but it is the base for both of these terms. So you're really just multiplying A bunch of times. So just like with the integer bases, the variable bases stay the same, and you're simply adding the exponents' values. 10 plus 13 is 23, etc. Now, what if you had a problem like this right here? I'm going to let's say we have 5 to the 8th power times 5 to the bth power. How could you simplify that? What do you think? Give yourself a minute. Give yourself a minute. See if you come up with an answer. Some of you are saying, no, we can't simplify this because we can't add A and B together. And that's true. We don't know the value of A and B. We can't add them. But we can write it like this. 5 times 5 to the A plus B power. Which is true if these were numeral values. We would just add them together like we were doing over here. But since they're not, we can just write it as A plus B. Very good. Okay, so there you go for number 7. Talk about number 8. Once again, these rules are true because the bases are similar in all of these expressions. If they were not, you could not add the exponents together. But what if instead of having just 2 terms in the problem, what if and let's come down, you're turning the page maybe to exercises 9 and 10. Let's just look at 9 and 10. Don't go to 11 yet. So 9 and 10. What would happen if there were more terms with the same base? Write an equivalent expression for each problem. So what happens here? 90 seconds. Go ahead. Some of you may have said that nothing changes, right? Because really we're just multiplying, in this example, we're multiplying 9 a whole bunch of times, right? And we just continue that. And we know it's this many number of times. So 9 to the 4th plus to the 6th plus to the 13th. And we add all those up to get us 9 to the 23rd power when we add up all the exponents. So again, the bases were similar for all of these terms. We were multiplying them together, so we added the exponents, right? So look at exercise 10. We have similar bases for all the terms, so the base is going to be 2, and we're just going to add all of these exponents together. So we have 3 plus 5 plus 7 plus 9, 2 to the 24th power. So we've learned the rules for when the bases are common and we're multiplying numbers in exponential form. But what if, and if you've looked down at your page, you probably have already seen exercises 11 through 17 here, and seen that in these expressions, we don't have completely common bases. Well, what's happening here? Using the commutative property, since everything here is being multiplied together, we can simply move, for example, this 6 to the 14th power. We can take it and move it over here to the front, right in front of this 6 to the 5th. And what we have now is just this problem in a slightly different form. So now we can see that we have common bases right here and here, right? We have a 6 and a 6. So since they have common bases, we're multiplying these together. We can add the exponents of these 6's. 6 to the 19th power. And here we have 4 and 4 common bases with 2 exponents that we can add together, 9 and 3, 4 to the 12th power. And again, we're still just multiplying all these things together. So we're multiplying 6 and 4 together. Now, we could simplify this in one more way by writing it in its numerical form. We could actually figure out what 4 to the 12th is and what 6 to the 19th is, and then multiply those numbers together. But in this exercise, that's not what we're doing. All we're going to be doing is putting the like bases together and then multiplying. So we have 6 to the 19th times 4 to the 12th. All right, so we come down, we're going to do exercise 12 together, okay? And then I'm going to let you do 13, 14, and 15. So in this example, I'm just going to shorten this up a little bit. So I have 17 here. I've got 17 here. Everything is being multiplied together. So we can add the exponents for the 17s. We have 17 to the 5 plus 7. That's 17 to the 12th. And we are multiplying. The little dot is multiplication. We know that from last year, from 7th grade. And we have negative 4 to the 2nd plus negative 4 to the 3rd. So we have negative 4 to the 5th power. Very good. Simplify this any further because we no longer have like bases. So 13, 14, 15, 16. Give yourself 2 minutes on the clock right now. You're going to match up the bases and add them together. All right, so some of you may have stumbled on 13 because what is the exponent right here? What exponent does this 15 have? If we write 2 times 2, for example, 2 times 2 times 2, that would equal 2 to the 3rd because it's repeated multiplication. Well, 2 times 2 would equal 2 to the 2nd power. So again, it's just twice that we're multiplying. Well, if we have just 2, well, that's going to be equal 2 to the 1st power. So in this example, we have 15 or 15 to the 1st power. There is an implied 1 right here. So when we multiply these two 15s together, we're going to have 2 plus 1, 15 to the 3rd, times we'll have the 7s, add their exponents, 7 to the 6th power. What we have in 15 actually is 2 separate expressions. So we have 3 to the 7th times 9 equals 3 to the 7th times 3 to the 2nd power. 9 equals 3 to the 2nd power, right? 3 to the second power is 3 times 3. 3 times 3 is 9. Check. This is a truthful statement. Now they want us to simplify this statement right here. So we have 3 to the 7th times 3 to the 2nd. We can now add these figures together. Get 3 to the 9th. So by finding the square root of 9 here, we were able to rewrite this in a slightly simpler way. And if you look at exercise 14, that's what they did here again. They simplified 2 to the 4th times 8 to the 2nd, 2 to the 4th times 2 to the 6th. And so here's how this one breaks down. So let's take 8 to the 2nd power, and we're going to write it out over here. And we're going to start doing some factoring. So we could also say 8 is just like 4 times 2 times, since it's the commutative property, we don't need to have these in brackets or anything. We're multiplying everything. So we have, again, 2 times 4, which gets us 8 again. So we can simplify 4 even further into 2 times 2. We bring down the times 2, and we break out the 4 times 2 times 2. So 8 to the 2nd power is the same as 2 to the 1, 2, 3, 4, 5, 6 power. This checks out. We can even go further and actually multiply all these things together. So 8 times 8 equals 64. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2 again, 32. Times 2 one more time is 64. This all checks out. Good deal. So now we have this in exponential form with common bases. So the 2 is our base, and we just simply add the exponents. 10 and 6, 2 to the 10th power. 4 plus 6 is 10. My lines are right there. Okay. Exercise 16. What did y'all come up with? I want to know. Yeah, if you said this cannot be simplified, that is exactly where we're going with this. Cannot be simplified further. Simplified further. Why? Why can't this be simplified any further? Well, we don't have any common bases, right? And we can't break 5 into any kind of 2, right? We certainly can't do that because 5 is an odd number, 2 is a prime, 5 is a prime as well. So there's no simplifying this any further. This is our final answer right here. Okay, so moving down to exercises 17 and 18. This is a very dense lesson. We're going to be learning a lot of the rules of exponents in this one. What we have to learn about, though, is some vocabulary before we move forward to exercise 17 and 18. First is the term monomial. Okay, so monomial. You may see this written as word term. You may see this written out as the word term. Okay, a monomial and a term are the same thing. Okay, they're equivalent, right? Okay, so monomial or a term is a number. Remember, the hashtag is the sign for number. A number, a variable, or the product of numbers and or variables. So the product, what does product imply? What do I mean when I say product? What's happening? Very good, multiplication. So when I say the product of things, that means those things are being multiplied. So let's come to exercise 17. what we have right here is a monomial because everything here is being multiplied. Everything inside of this term is being multiplied. Whenever we're dealing with a monomial, again, we can move the parts of the monomial around as we please. So we have 2 times x times, it's really x times x times x times x, right? We have x times x. I'll actually write all of that out. X times x times x. And then we're multiplying that times 17 and x 7 times, which write out with something like this. X times x times x times x times x times 7 times. Okay, all right, and using the commutative property, allows me to move things around when I'm multiplying, such as 2 times 3, which is equal to 3 times 2. These things are equivalent. That is the commutative property. So I can move things around as long as I am multiplying. So again, I'm multiplying everything. I'm going to go stick this 17 right in front of the 2 right here. So I'll have 17 times 2 times x this many times, right? Which I have how many x's? I multiplied it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times, right? 3 plus 7, x to the 10th power. Okay, so now I have 17 times 2 times x to the 10th power. Well, I can't combine any more exponents, but I can actually multiply 17 and 2 together, right? I can multiply 17 times 2 to get me 34x to the 10th power. So again, here we didn't add the exponents of 17 and 2, right? We literally just multiplied 17 times 2, which we could, if we wanted to go back to, like, let's say this example, we could actually multiply 15 times itself 9 times. I can come grab my calculator here. I can do that for you. 15 times 15, do that. Oh, I could actually do that pretty easy. It gets pretty big. So in these examples, it's easier to keep these numbers in their exponential form, right? Well, this one wasn't. You get what I'm saying. We could simplify all of these numerical expressions further by actually multiplying them out. But we're keeping these in exponential form as much as possible. All right, so let's come back down and let's continue to talk about monomials and polynomials. So, polynomial. If you know anything about Latin, these words, maybe you've seen them before. We have monomials, which is the product of a number or a variable. A polynomial is just multiple monomials. Technically speaking, they are the sum of multiple monomials. So the sum, meaning that we are adding them together, right? Sum implies addition. So let's take a look at exercise 18. It says, let A and B be numbers. Use the distributive law to rewrite the expression in a simpler form. So what we have here is a polynomial because we are breaking these things up by an addition symbol. And since we cannot add A and B together, we just can't do it because they are not the same base. Since we can't add A and B together, this will ultimately be a polynomial. Now, in this problem, it's actually just asking us to use the distributive property to rewrite this expression. So let's do that, okay? What is the distributive property? What does that do? The distributive property allows us to do this right here, okay? So if we have 2 times 3 plus 4, that's actually the same as saying 2 times 3 plus 2 times 4. And we can actually prove that out. So using order of operations, in this example, we would add 3 plus 4 first to get 7 times 2, which would be 14. And over here, we would have 2 times 3, which is 6, plus 2 times 4, which is 8, which equals 14. And this is also true if you were to, say, do these with variables, such as in exercise 18. Here we have a times a plus b, so we would just distribute the a inside of the parentheses, just like we did over here with the 2, only this time we're doing it with a variable, right? Well, what's a times a? Well, a times a, we could just write it as a times a, right? We could write a times a. And then we have a times b, and again, this is separated by the addition sign. So we are adding these terms together, these monomials together to create a polynomial. And so we have a times b, which is a times b. Well, this can still be simplified because we have a times a over here in this term. And when we have similar bases, we can add the exponent. And what is the exponent of the a's? Well, there's an implied 1, right? Just like we demonstrated above. So when we add their exponents, we get a times a, which is a squared. And just think about it in terms of regular numbers, right? 2 times 2 is just the same as saying 2 to the second power. So a times a is a to the second power. We are adding these things together. This is a polynomial, so we have a squared plus ab. This is our final simplified answer for 18. We're covering a lot of rules in this lesson. So given what we learned from exercise 18, I want you to try exercise 19. Cool, very cool. Thank y'all for your effort. So we're going to distribute the b inside of the parentheses, and we're going to multiply both parts. B times a would just be BA, or we could say AB if you wanted to keep it in alphabetical order. Again, we're multiplying this term, so the commutative property lets us change it to AB if we want to. And then we have B times B, which is just B squared. And we can't add these together because we don't have similar bases. Because AB is not the same as B. So this is as simplified as this gets. All right, now question 20. Okay, well, I want to go over this one together. So question 20, we want to let A and B be numbers. We're going to use the distributive law to rewrite the expression in simpler form. Okay, now this gets a little bit tricky when we do polynomials times polynomials. And these are polynomials. We can't simplify them into monomials. We don't know what A and B are, so we can't just add them together. Now, instinctually, maybe you wanted to write A plus B times A plus B is just 2A plus B, right? This is not the case. This is incorrect. It's actually a little bit more complicated than that. And I can demonstrate this. I'll demonstrate this right above here. So let's say we have A. Let's make A equal 2 just for simplicity. B will equal 3 for simplicity. So we have, in this example, we have 2 plus 3 times 3 plus 2. Yeah, right there. No, it's 2 plus 3 plus 2 plus 3, so let's not. Times 2 plus 3. Order of operations, we do what's in these parentheses first. Add 2 plus 3. 5 times 2 plus 3 is 5. 5 times 5 is 25. So this is not the same as 2 times 2 plus 3. In this case, we would have 2 plus 3, which is 5, times 2, which is 10. These things are not equivalent. What we can do instead is distribute both parts of the polynomial into both parts of the second polynomial. So take a first, okay? Since it's at the beginning of this term, we have a times a. So we have a times a, which is a squared, and we're going to be adding that with a times b from the second polynomial, which is ab, plus, now we're going to multiply the second part of the polynomial, b times a, which is ba, times b times plus b times b, which is b squared. So now we've turned this into a polynomial with more parts, but we can simplify this further. Since a squared is its own base, there's no other base like it, we're going to keep it by itself. We have a squared right here. And then we have b squared over here, which is the same. It's all by itself, so we're going to be adding a squared plus b squared. There's no way to simplify that any further. But what about ab plus ba? Well, we talked about how we can rewrite ab to equal ba. So we can rewrite ba as ab, and we could have it as ab plus ab. Now, here we actually have common bases. We don't know what AB is, but it equals AB. So AB plus AB is going to equal to AB. We can treat it as one term. We can now simplify this part of the term into plus 2AB, or you could say 2BA. I like to keep it in alphabetical order just because it's nice and neat. And we're going to prove that this is most definitely the case. So here I am suggesting that A plus B times A plus B equals A squared plus B squared plus 2AB. So I'm going to come over here and I'm going to see if that's true. And I'm going to use my example again of A equaling 2 and B equaling 3 just for an example. So we have 2 to the 2 squared plus 3 to the second power, 3 squared, plus 2 times 2 times 2 times 3, as suggested down here. Okay, so let's work this out. 2 times 2, 2 squared is 4. 3 times 3, 3 squared is 9. Plus 2 times 3 is 6. 2 times 6 is 12. Let's add these all together. 4 plus 9 is 13. Plus 12 is 25. Big old checkaroonie. We know we got that one right. So we have proven that this is most definitely the case, and that this is a simpler form of this. A natural consequence of exponential notation is that when since we're able to add exponents when bases are common, that we can subtract them when we divide them. So in exercises 2 through 21 through 24, right here on your next page, at the bottom of this page, right here, we see some examples of this. So we have 7 over 9 divided by 7 to the 6. So whereas we were adding when we multiplied, here we're dividing, so we subtract 9 minus 6, which is 3, 7 to the third power. And again, I'm going to use some really simple numbers to prove that this is the case. So let's use 2 again, 2 to the 4th over 2 to the 2nd power, let's say. Right? So 2 to the 4th power is actually 2 times 2 is 4, 4 times 4 is 16. 2 to the 4th power is 16, 2 to the 2nd power is 4. So we have 16 over 4, which equals 4. Now let's try this using this method. So instead we're going to subtract these bases. We have these exponents, I should say, 4 being divided by 2 to the 2nd power. We have 2 to the 4th power being divided by 2 to the 2nd power. So we subtract 2 from 4, and we get 2 to the 2nd power, which is equal to 4. So we proved that this is the case. Okay? Here in exercise 23, 22, and 24, I want you to see if you could come up with some solutions. Give yourself 90 seconds, and we'll come back. All right, great work. So you should have come up with something that look like these answers right here that I got for you. We have 8 over 5 to the 7th. Again, you're just subtracting 2 from 9 to get 7. 16 minus 7 gets you 9 right here. So you have negative 5 to the 9th. And it is important that you put the negatives into parentheses like that right here. Here we have 5 minus 4, which would get us 13 to the 1st power, or we learned that 13 is an implied 13 to the 1st power. So you could write this as 13 to the 1st power or 13, either way. So exercises 25 and 26 are very similar. They just say, let A and B be non-zero numbers. And we talked about this. Don't freak out about the variables being here. That's your base. A over B is your base. You have, what is the following number? So solve these two. They're the same as the other ones. 30 seconds to figure it out. 26 was very similar to 24. We have 5 minus 4, which gets us x to the 1st, which equals x. So either one of, if you wrote that either way is fine. Then we have a over b, and I know that my a's look like 9s. I know that, guys. A over b in parentheses to the 7th power. You're subtracting 9 minus 2 to get you 7, and a, b needs to be in parentheses here for it to be correct. That is crucial for fractions. Okay, come down, and let's look at 27 through 30 all together, because this is just a kind of a collaboration of some of the ideas that we've already gone over. If you want to challenge yourself, you can pause the video right here and give yourself a challenge. Otherwise, I just want to move forward and talk about all of these together. So 27, we see again, we talked about 4 squared and 2 to the 4th power. Those are equal. We proved that y up above. So they just turn 2 to the 7th over 4 squared into 2 to the 7th over 2 to the 4th power. So now that we have common bases, we can subtract the exponent. So here we would have 2 to the 3rd. 7 minus 4 is 2. 7 minus 4 is 3, and we maintain the base, right? So 2 is still there, and we just change the exponent by subtracting them based on our rules of exponential notation. All right, so exercise 29. Now, this, it looks like it would be a little bit more complicated. Yeah, I don't disagree with you, but we're simply going to be subtracting the exponents of the common bases here. So in this case, we'll be simplifying 3 to the 5th over 3 to the 2nd power into 3 to the 3rd power. And we subtract the exponents for the 2's. 8 minus 3 is 2 to the 5th power. And we were just multiplying these together anyway, so we could write this like this in parentheses. 3 to the 3rd times 2 to the 5th. And we could actually simplify this one pretty easily. Neither one of these, this isn't going to be actually a very large number. Why don't we actually do that? Give me a quick second. So if we were to calculate this number right here, we take we can multiply 3 times 3 times 3, and then we multiply that times 2 times 2 times 2 times 2 times 2, 5 times. So yeah, that's not actually that big of a number or anything. But I don't actually need this, but it is that number just to show it. And then here, this is very similar to 27. It's probably why it's 28. I go all over the place. I apologize for that. But it's just telling us 27 is equal to 3 to the third power, which it is. We showed that earlier. 3 times 3 is 9. Times 3 is 27. So these things are equal. Anyway, so now we have common bases. They both have a base 3. So we can subtract the exponents. Because we're dividing them, we subtract. So we have 3 as the base. 23 minus 3 is 20. So 3 to the 20th power. Right? Okay, so then you're going to match up your common bases right here. And I want you to give me an answer. Give yourself 30 seconds. Try to come up with it. Very good. And actually, this one, again, I probably wouldn't keep it in this fashion anyway, because we could probably do this pretty easy. Negative 2 squared is 4 times this would be 380, I'm pretty sure. But anyway, this is how they would want you to write it anyway. So, exercise 31. So, exercise 31, let x be a number, write each expression in a simpler form, a, b, and c. I want to give you some time to see if you can come up with something. Take some time and try to see if we can come up with something. You'll come up with some really interesting answers. I really appreciate your hard work. Let's take a look at this together now. So we have 5 and 5 over x squared. That's being multiplied times 3x to the 8th power. Now, we can always write 3x to the 8th power as 3x to the 8th power over 1. Remember our rules of fractions from 7th grade. So we can put this as a fraction over 1. Anything divided by 1 is just that number. So this doesn't actually change anything, but what it does allow us to do is multiply this as a fraction. So now we can multiply x to the 3rd power times 1. That will stay in our denominator, and we will multiply 5 times 3x to the 5th. So really we just have 3 times 5 times x to the 8th. So we have 3 times 5, which is 15. We're multiplying the numerals there. 15 times 3, x, 8. And sometimes having x as a variable can be confusing because it looks like you're saying 3 times 8 right here, but no, we have 3x to the 8th power. Okay, so from here, so we have 15x to the 8th over x to the 3rd. So what we can do is take our common bases, which x has a common base right here, and we can subtract 8 minus 3 to get us x to the 5th. Well, what about this 15? It doesn't seem to have a partner, does it? It doesn't seem to have a numeral partner. Well, again, here we can have an implied 1. Multiplying 1 times anything doesn't change anything. So we have 1x, which we did. We just had 1x times 1x to the 3rd power. But here now we can just say 1 times x to the 3rd power and it doesn't change anything, right? And now 15 has a numerical value. It's an implied 1 underneath here in the denominator. 15 divided by 1 is 15. So our final answer would come up, our simplified answer would be 15x to the 5th power. And for B and C, they're going to ask you to do the same thing. Let's take a look at B together quickly, and I'll let y'all work on C individually. Okay, so B, again, we have 5 over x to the 3rd power. That's being multiplied. Put a little dot here for multiplication. The dot is also multiplication. Remember that from last year. We have times negative 4x over to the 6th power, I should say. And we'll put all of that over 1. so that it's a fraction. Now we can multiply denominators and numerators. 5 times we're multiplying it times the numeral here. We can multiply the numerals together. Negative 4 times 5, negative 20. Remember your rules of multiplying negatives. So we have negative 20x to the 6th power over x to the 3rd power times 1, which is just x to the 3rd power. Okay, so now we have negative 20x to the 6th over x to the 3rd. We're going to divide the common factors in this monomial and the common factors right here for the numerals. We have, again, an implied 1 right here. Just like when we divided by 1, that didn't change anything. When we multiply this by 1, it doesn't change anything. It just gives us a partner for 20. So we have 20 over 1, which is 20. X to the 6th minus x to the 3rd is x to the 3rd. That's what a final answer would look like. So try C independently right now. Go ahead. Give yourself 90 seconds. And there is C all worked out right here. I talked about it. It's the same steps for problems A and B. So there you go. You can check your answer. Good work. I appreciate your hard work. So this is definitely a dense lesson. You're going to have a lot of notes for this. Move forward to problem set. You can use the rest of class period. Remember to check your rubric for how to respond to these questions. I have faith in your ability to do so. Yes. I absolutely have faith in you. Do your best. Remember to check your rubric on how to respond to constructive response questions. Fantastic. Thank y'all for joining me. See y'all in the next one.